Go.
Yes, we are. Thank
Oh,
you.
thank you for this invitation. I should just add a little to my history. I was an undergraduate, as you learned, at the University of Manitoba. One of the professors there, Ken Standing, had been a graduate student at Princeton, nuclear physics. He determined that I must go to Princeton. I did. Welcomed there by two other people from the University of Manitoba. Bob Pollock was a year ahead of me. We were good friends at Manitoba, and he and Jean and Elson and I remained good friends afterward. The other, Bob Moore, a few years earlier, I didn't know him until I got to Princeton. Bob Pollock was a true genius at experimental physics. When I arrived, one of the professors, Donald Hamilton, sought me out to see if I was another Pollock. A short conversation revealed that I'm not. We parted as good friends. Bob Moore was working with Bob Dickey, Professor Robert Henry Dickey. He had decided that gravity physics was shamefully neglected in physics at the time. He started a program that became very rich and was largely responsible, I would say, for the importance of research in gravity physics these days. Bob Moore took me to Bob Dickey's research meetings. I was entranced. It was Bob who suggested to me that I start looking into cosmology. I was more than a little uneasy about that because at the time, cosmology was mostly a melange of ideas with very little evidence, a very dicey field, but I could see a few things to do that led me to other things. One thing led to another, and so I spent most of my career in this subject and saw it grow into a remarkably rich field. Anyway, let us start. I should explain also that I've been giving lectures in cosmology for over half a century. A lot has changed in that time, an immense amount, but some things haven't. And for old time's sake, I will start. Do we now see this image from times past? It hasn't changed much. We're still in a solar system with the sun, Earth, a rocky planet, Jupiter, the main planet.
Excuse me, Professor. So you have to go to share screen at the bottom of your screen.
Okay, I see. Let me share screen. Now, what do I see? Now I click on this, do I?
Perfect.
Now we can see it. I can expand it. Good. Now you can see it? Hello?
Yes, we can see it.
Okay. Just to remind you that Jupiter has roughly the composition of the sun. It's not a star because it's not massive enough. If it were maybe a 20th of the mass of the sun, it would be shining. You will remember that here's a modern image of Jupiter. It's not a star, it's not generating energy, but it's cooling off. Currents of gas rising up from the center where it's hot, combined with rotation, turns streams into swirls. You see the great red spot. Am I able to point it? Yep, the great red spot, been there for a couple hundred years. Fascinating object. Another fascinating object, Saturn's moon, Europa. Looks like it's got a sea of water covered by ice and cracks. And here is the sun. Main lesson from those two images is you look in different places, you're apt to see new and interesting things. So let's look at the neighborhood of the sun. Here in this map, the sun is toward the center. The sizes of the spheres are proportional to the actual physical size of the star. Of course, the sizes are greatly exaggerated relative to the distance between stars. Anyway, you see that the largest star in this neighborhood is Sirius A. It's about twice the mass of the sun. The greater mass makes it much higher pressure in the center. That makes it go much more quickly. This is shining at 25 the luminosity of the sun. Procyon A is about the same, about intermediate size to the sun. I should remark that the high luminosity of Sirius means it's burning its supply of nuclear fuel more rapidly than we are. It will, in cosmic times, die pretty soon, collapse, and may form a white dwarf. You see the dot just beside Sirius A, that's a white dwarf, Sirius B. Sirius being luminous has also a hot surface. Hot is blue. Many of the stars in our neighborhood you see are smaller than the sun. Surface is less hot, they're red. These lines indicate a guide to how you can go to different places. If I go to the right to this point and then out of the blackboard to here and then down, I come to Proxima Centauri. It's kind of interesting because it is a planet. The planet is just about in the Goldilocks region, not so hot that water on the surface would boil, not so cold that water would freeze. Wouldn't you just love to see what's on that planet? And of course, you can imagine people are talking about how to get there, at least in small robots. Here's the distribution of stars in our galaxy, the Milky Way. You see the rifts of dark. That's not absence of stars, but rather presence of gas, of dust that obscures starlight. Here's another galaxy of stars quite nearby that is a lot like the sun, a lot like our Milky Way galaxy. I might just point out the blue regions. When stars form in a group, there tends to be a few large ones. They're very bright and blue. That makes these blue patches. These young massive stars that are so luminous tend to emit ionizing radiation that ionizes the interstellar medium. Ionized plasma, mostly consisting of hydrogen, emits a sharp line at 6,600 angstroms. That causes the red patches you can see here and there. Fascinating. You see the dust lanes, elegant spirals. You see a sheen of yellowish light across the center. In this contrast, you don't see it, but it's throughout this galaxy. That's the light of some 10,000 million stars, similar roughly to the sun. The astronomers find that in our neighborhood, in our Milky Way, there are at least as many planets around stars as there are stars. We can be very sure then that in this galaxy, there are some thousands of millions of planets on which all sorts of wonderful things are happening that we, the human race, will never see. Wow. Here is another galaxy of a different sort, an elliptical with a disk in it, yet another galaxy that's just a gas of stars. And here is our neighborhood of galaxies. You can see, I hope, the red dots. Those are galaxies similar to the Milky Way. I show 4 examples at the bottom, 1 elliptical and 3 spirals. You see a lot more stars that are much less luminous, much less massive than the Milky Way. It's interesting that they're arranged in a sort of sheet. This is 2 views of the local distribution looking at perpendicular directions. And you see a great region up to the upper left that's just empty. Apart from a couple of galaxies, one is pictured here. This is a Hubble telescope image. You see it's this wimpy little thing. It has a few bright spots in it. They may be regions where stars are forming, a little hard to tell. Maybe you can make out the contours around the HST image. It's a cloud of hydrogen around it, a fascinating object. Fascinating too, to consider how clumpy the distribution of galaxies is. The great concentration along this plane, the almost dead empty region above it, clumpiness. And I just unplugged my power so I might lose things because this is getting kind of old. Here is a distribution of galaxies on larger scales. You see again the clumpy distribution, bumps and wiggles. This is the pattern of the large-scale nature of the universe. You see in the center a particularly bright spot. That's the Coma cluster of galaxies. It is a galaxy of galaxies. That's fascinating. But what's also fascinating, you notice, is that this part looks a lot like this part. We can see an even more extreme case of this by looking at radio galaxies. Here's the nearest nearby one, very bright radio source. The galaxy is buried in here. Violent relativistic jets have been blown out of the center of the galaxy. Here, radio emission in these great lobes. This is a phenomenon that can be seen at great distance. And so a map of the distribution across the sky of the 10,000 or so of these most luminous radio galaxies shows you this picture. I have to caution you, ignore the hole in the center. The telescope can't reach that. Ignore the dot down here. This is Cygnus A. It's so bright that it dazzles the telescope. It can't see sources around it. I'm not sure why this hole is here. It must be another bright radio source. There's also a band of sources along here. They're relatively faint things in the plane of the Milky Way of our galaxy. So ignore all those complications. Also, this part that's incomplete up here. And what do you see? Well, you see something new. You notice that as you go to ever larger scales, you see ever different views of the universe. Things change. Of course, that hierarchy of structure goes down too. We can talk about the cells and bodies of us, and we can talk about the atoms in the cells and the atomic nuclei and the atoms and the quarks in the atomic nuclei, structure upon structure. But here, as you look to ever larger scales, you stop seeing anything new. The key point then, the universe on large scales looks awfully close to uniform. That is why we can presume to make a theory of the universe rather than of one or another of its hierarchies of structure. If the universe is the same everywhere, then we have a pretty simple game to play. How is the universe everywhere evolving? A simple question in principle, and in fact, not so bad in practice. Now, the expanding universe, just to remind you of the idea behind the expanding universe, imagine we lived in 2 dimensions on the surface of a balloon. You must not ask, what about the space away from the surface, above, into the balloon or out of it? You don't ask that question because you live in 2 dimensions. That's your world, 2 dimensions plus time. These squiggles are meant to be galaxies. You notice that if this balloon weren't being blown up, you could start walking in one direction. You come back to where you were, you would see the same universe everywhere on average, aside from the local fluctuations. It's a homogeneous universe. But now, I will get back to this text and this curious figure later. Now, just imagine the balloon is being blown up. You sit on a galaxy, you look around you, you see that the galaxies around you are moving away from you. You may say, wow, the universe is expanding, and it's expanding away from me. But of course, every other observer would see the same thing. This is the nature of the expansion of our universe. Kind of interesting to look at some of the people who were responsible for finding that the universe is expanding. I begin with Percival Lowell. He was of the very socially prominent and wealthy Boston Lowells. You may know that verse. So now we are in Boston, the home of the bean and the cod, where the Lowells speak only to Cabots and the Cabots speak only to God. He was one of those Lowells. He had a fortune. Astronomers honor his memory for deciding to use his money to build an observatory and hire excellent astronomers to check on whether there might be canals on the planet Mars, built by an advanced civilization that was running out of water. Well, there was water on Mars, but not of the sort Percival was looking for. Anyway, he did a very good thing. He chose a good place to build his observatory. He hired excellent people like Melvin Slifer. Melvin built instruments that allowed him to show that the light from distant galaxies is shifted toward the red, as if the galaxies are moving away from us. That's the expanding universe. Henrietta Leavitt, down the lower left at the observatory in Harvard College, discovered a very useful way to get distances to galaxies, Cepheid variable stars. have a variable brightness, a sharply defined period. She showed that the period is a good measure of the intrinsic luminosity. So if you ask yourself, how bright is this star in the sky? You have a good estimate of its distance. Lower right, Edwin Hubble, who had just the right instincts for the time, and his assistant, Milt Hubbleton, who had just the right technology to do what Hubble loved to do. On the theoretical side, the German Hermann Weyl was maybe the first to decide that maybe the universe is expanding. He is a brilliant mathematician, driven out of Germany by the Nazis, ended up in Princeton. But he didn't have a real theory. He had a scheme. Alexander Friedman, the Russian, knew the theory, found a solution in Einstein's general relativity theory for an expanding universe, but he didn't know about the astronomical evidence. It was Georges Lemaitre on the right, Belgian, who in 1927 put together the theory, which he'd independently discovered, and the observations to make the outlines of the present theory of the expanding universe. So that's the beginning of our subject. I want now to describe an event that happened in the years after the Second World War. The end of the war released an enormous amount of energy in science and technology. It gave us automobiles with fins. It was all kinds of things. It's still continuing. The revolution goes on. But of course, along with this advance in technology, there were advances in ideas about science, and it marked a second golden age in cosmology. The first, I would say, the years around 1930, when Georges Lemaitre was the one person, I think, who understood best Einstein's theory and its application to general relativity and to the expanding universe. These were the people involved in the second golden years. Second from the left, George Gamow was the most impressively imaginative, inventive of the lot. With imagination, alas, comes a certain tendency to be indifferent to details. He had brilliant ideas, but he didn't quite carry them through. Fred Hoyle, to his right, to our right, brilliant in Cambridge, England, brilliant discussions of how stars are made, how the stars make elements and distribute them. He was one of the co-inventors of the steady state cosmology. You recall that one postulates that matter is continually created. So as the galaxies move apart, new ones form. The universe is in a steady state. He liked that theory. He disliked Gamow's theory. Alas, he was a very stubborn person, and he couldn't. But my impression from just a few conversations is that he felt the distance scales and the time scales of cosmology are just so large that you'll never empirically establish a cosmology. You've got to do it by philosophy. The steady state theory really is philosophically elegant, but wrong. He was never able to admit that. A shame. On the outside, Bob Dickey on the left, Yakov Zeldovich on the right, both were involved in war research during the war. Bob in the left, radar and like technology of electronics that made such a big difference to the prosecution of that war against Germany. Zeldovich on the right, behind the horrible battles in the Soviet Union, was part of the Soviet development of atomic bombs. He played a big role in the Soviet hydrogen bomb. It meant that he had a lot of influence. He had the coveted Socialist Hero Worker Medal that he could flash before bureaucrats and get lots of things done. It also meant, of course, that he couldn't leave the country because he knew all these secrets. So let's begin with Gamow. He had the idea, 1948, that the universe might have expanded from a hot, dense state. Thermonuclear reactions in the very hot early stages would have produced elements. And as the universe expanded and cooled, would have formed galaxies. He was a real pioneer of these ideas. Two consequences in particular of his idea: there would be a sea of thermal radiation left over from those early days. It would be cooled by the expansion, but it would maintain, we would remember its thermal spectrum. And he also understood that this hot Big Bang would produce a lot of helium. As it happened, 1941, Andrew McKellar, Dominion Astrophysical Observatory, Victoria, British Columbia, analyzed some observations that indicated that in interstellar space there is the molecule CN, cyanogen, carbon and nitrogen stuck together. Not so healthy, but it's elegant to look at in interstellar space. You'll recall that a molecule can have discrete energy levels of rotation. The astronomers had noticed absorption of starlight by cyanogen from the ground level and also from the first excited level. Why is it there why are some of the cyanogen in the excited level? That excitation is about what you would expect if the molecules were in a sea of thermal radiation at a temperature of about 2.3 Kelvin. Tantalizing, because Gamow and his group for a while were thinking of a temperature around 5 Kelvin. That's twice that number, but you know, both were very uncertain. And in fact, the measured temperature is about in between. Fred Hoyle knew very well Gamow's theory. He reviewed a book in which some of Gamow's ideas are presented. Fred thought this was a terrible thing to do. He said, among other things, this notion of Gamow's about a hot Big Bang would lead to a temperature of the radiation at present maintained throughout the whole of space, much greater than McKellar's determination for some regions within the galaxy. Well, much greater, a factor of 2. Within the uncertainties, that isn't so much greater. Remember McKellar, 2.3 Kelvin. Helium. George Gamow understood that helium would be made in abundance. Here's his calculation on the left. On the right, Enrico Fermi, Anthony Tricovich knew a lot more nuclear physics. Fermi came out of the US nuclear energy program. Their computation, helium would amount to about 1/3 of the mass of the universe. The other 2/3 hydrogen. Helium, some remembered that. Here's Martin Schwarzschild on the right. In a discussion at the Vatican Observatory on elements production and star populations, and then Fred Hoyle saying, the difficulty about helium still remains, however. They're wondering how it was produced and distributed. Martin Schwarzschild, the evidence for the increase in heavy elements with the age of the galaxy supports the idea that elements were formed in stars. As the stars grew and exploded, the abundance of heavy elements would increase. It was observed that there are far fewer heavy elements in older stars. However, he said it does not necessarily mean that helium production occurs mainly in stars. Gamow's mechanism may work up to mass 4. Hoyle, this is 1957. That is why a knowledge of the helium concentration in extreme population 2 is so important. You recall POP2 means very old stars with low abundances of heavier elements. If there were a lot of helium in these population 2 stars, you would wonder where it came from, if not from the hot Big Bang. 1964, astronomers had pretty convincing evidence that the abundance of helium is much larger than seemed reasonable for production in stars. Hoyle disliked the Big Bang model, as I've said, but he, with Taylor, pointed out that this helium could be from Gamow's hot Big Bang. But Hoyle once knew that the cyanogen suggested an excitation temperature of a few degrees Kelvin, but by 1964, he'd forgotten it. I've forgotten lots of things. Meanwhile, in the Soviet Union, Zeldovich had moved away from nuclear weapons and had started very imaginative work in cosmology. Here he is with 2 other Soviet scientists. They were working in science under very difficult conditions. As I said, Yakov Zeldovich couldn't get out of the Soviet Union and talk to people in the rest of the world. Journals were heavily censored before they could be read. That meant they were always far behind time as to what were happening and being reported in the journals. They couldn't publish in journals that people outside the Soviet Union were reading with any frequency because the censor prevented that. Yet these people were very intelligent, very smart, and they were doing great science. But Zelzovich didn't have the advantage of interactions with many observational astronomers. He had formed the opinion that the abundance of helium is quite low in the oldest stars. That meant a low abundance, that Gamov's hot Big Bang theory has to be wrong. Meanwhile, in Princeton, New Jersey, here left to right, Dave Wilkinson, me, Bob Dickey. This is a few years after 1964, when Bob had said to three of his young people, Dave Wilkinson, me, and Peter Roll, why he thought it would be a good idea to look for thermal radiation from a hot early universe. He and we didn't know about Zeldovich or Hoyle or Gamov. We just thought it would be a good idea. Here is David Wilkinson holding the screwdriver, Peter Roll, you can just make out in the plaid shirt, and a radiometer built to look for this radiation. Meanwhile, 30 miles to the north of Princeton, at the Bell Telephone Laboratories, 1959, people started working on communication by microwave radiation. Here, an early experiment, but a very sophisticated detector inside that shack. You notice that it's a crude system. There are rough planks holding up this antenna. To make the numbers balance, these people had to assume that about 2 degrees Kelvin is creeping into that horn from somewhere, maybe from the ground. That was a true fudge because these antennae are designed to be very efficient at rejecting background radiation coming in from the sides, the back. They had an anomaly. That anomaly remained a dirty little secret at Bell Labs until 1964, when Arno Penzias on our right and Bob Wilson, another of those horn antennae, were resolved to understand where that extra noise was coming from. They had exhaustively searched for possible sources. They were getting very frustrated when at last word got to them of the experiment at Princeton, and things came together. Now, I just have to summarize this lovely situation. In the USSR, Zeldovich thinks Gamov is wrong because of low helium abundance. In the UK, Hoyle knew the evidence that the helium abundance is large, about what you'd expect. He knew, as I said, about the evidence from cyanogen, but he forgot it. In the USA, we knew nothing of these guys. We only found it would be interesting to look into a hot Big Bang. And as 1964 grew to a close, they were about, Wilkinson and Roll were about to announce their results of detection. Meanwhile, at the Bell Laboratory, Penzias and Wilson were trying to understand why there was this excess noise. Early 1965, it all came together. Everything clicked. This is an interesting situation that sociologists of science know about. We know about it too, but we never think about it. That often when a brilliant idea appears, there's a good chance that someone had already thought of it or is going to think about it independently. Merton, a sociologist at Columbia University, gave this the name multiples in scientific discovery. It happens somehow. I don't think, I'm not at all thinking of extrasensory perception, but I think somehow we as a community communicate with each other in ways that are not exactly spoken or written. Ideas pass around, and somehow it has to be that, that often people have multiple ideas occur because people are communicating in ways that we don't quite keep track of. Anyway, I think this is something of this sort must have happened here. All these people coming together so wonderfully coincidentally. Here was a situation in 1966. Penzias and Wills had a measurement of the intensity of this radiation at a given wavelength. Princeton, the intensity at a different wavelength. If this is the thermal radiation you'd expect coming out of the hot Big Bang and cooled by the expansion, it would follow this solid curve. Well, it looked promising, but you would really like to see the whole curve. That was done, and I should just show you a picture of the people who did this. You'll see why in a moment. Here's one group. Kobe is the cosmic background explorer. Here's David Wilkinson. I don't know whether you can see him behind this thing here. Here's John Mather, who got a Nobel Prize for being the leader of this experiment. Here is a competing group. This experiment took 15 years to complete. Herb Gush, University of British Columbia, west coast of Canada, I don't need to remind you, for 15 years had been working on the same problem. Here are a couple of his two collaborators in the end run. Mark Halpern on the left, Ed Wishnow above. I always love to show this slide because it so amuses me to ask myself, if I didn't know that these two were part of a truly great accomplishment, if I only knew what I saw by looking at this image, would this image inspire confidence? Which of course is a great illustration of why you shouldn't make such judgments. Anyway, here are the results, both completed within a couple of months after 15 years of hard work. This is not a multiple, this is, I think, just a coincidence. Or I don't know, maybe not. It happened. Either one made the case. Yes, this radiation has the distinctive form of thermal production. The universe as it is now is incapable of forcing radiation to relax to thermal equilibrium because the universe is transparent to these wavelengths. The radiation just propagates freely. Herb Gush was fully deserving of the knowledge of the Nobel Prize. He didn't get it. Canadians sometimes are a little too diffident. He should have been more self-advertising. Anyway, we come to another point. Einstein's cosmological constant. Einstein took it as a matter of course that the universe is static. It's there forever. Gravity, in his theory, tends to pull matter together and to cause the universe to contract. To fix that, Einstein introduced his cosmological constant that has the property that it pushes matter away. So Einstein's idea was that the pull of gravity was going to be balanced by the cosmological constant to make a stable, static universe. It was the Belgian Georges Lemaitre who realized that this balance is quite unstable. Touch the universe, it's going to start expanding or contracting. This cartoon came after an article written by Professor Dr. Willem de Sitter, director of the Leiden Observatory in the Netherlands, 1930. What, however, pulls up the ball? What makes the universe expand or swell up? That is done by the lambda. Dutch is pretty close to English. Dot doet de lambda. Another answer is not given. This lambda was soon disfavored. Einstein came to hate it. Here is a letter from Lemaitre. Whoops, what did I do? Here is a letter from Lemaitre to Einstein, arguing that Einstein really ought to consider the cosmological constant. Einstein wrote back, since I've introduced this term, I had always a bad conscience. Down toward the bottom, I cannot help but feel it strongly, and I am unable to believe that such an ugly thing should be realized in nature. Wow. Alan Sandage set out to see if he could find this cosmological constant. These guys, Saul Perlmutter, Adam Rees, Brian Schmidt, the three on our right, received this prestigious prize, later the Nobel Prize, for their accomplishment in showing that accelerated expansion due to the pushing of the cosmological constant is real. I love this picture because, well, Sir Run Straw in the middle made a fortune in movies, Kung Fu and the like. Deeply respected until his death in Hong Kong and mainland China for his strong support for education. I love his suit. It's clearly bespoke. Here was the prime director of Hong Kong. His suit, it looks pretty good too. These guys, I've never seen them look so neat, but still, those suits were not bespoke. It pleases me to think that. Dark matter, Fritz Zwicky, an iconoclast, but a brilliant astronomer, physicist, already in 1937, saw that cluster of galaxies you saw, the Coma cluster in that map of the galaxies, as the galaxies moving about so quickly that this thing wouldn't be held together by gravity if the mass were all was in the stars. There had to be dark matter. Here is Vera Rubin. I don't know whether you can see her. Can you? Well, there she is anyway, doing measurements of the motions of stars in the outsides of galaxies. She measures what circular curves, one of many, but she, with her colleague about Kent, I'll get Kent later, had found that around nearby galaxies, the stars are on the outskirts are moving too fast to be held together by the matter you see in the stars. There need to be something faint, maybe totally dark, to hold these guys together. We have then this hint about dark matter. This dark matter was called upon for another reason. I should have to explain. In the early universe, it was hot enough to thermally ionize the baryons, the matter of which you and I are made. The plasma interacts strongly with radiation. Radiation is strongly scattered by free electrons Coulomb scattered by ions. The result is that plasma and radiation act like a fluid with high pressure. That fluid oscillates. Here you can see the effect of boundary conditions on an oscillating fluid. You notice the ripples line up with the boundary. In the expanding universe, the boundary condition is set in time. As the universe expands and cools to a temperature about 1,000 times the present value, the plasma it recombines. Radiation can no longer hold it in an ionized state. As the plasma recombines, it decouples radiation from baryonic matter, and the clustering of baryonic matter can grow. But meanwhile, up on here is the theory. Well, here's Jerry Yu, my first graduate student, Bob Dickey on our left, Dave Wilkinson on our right at a conference. He and I worked out the consequence of this oscillation and showed what you should look for. Somehow I forgot to put in here the other consideration, which I'm going to have to remember for the next time I use this. In the early 1980s, we knew that the thermal radiation, we knew it was, didn't quite know it then, it was thermal, but we're pretty sure, but it is very smoothly distributed. Meanwhile, we knew, as you saw earlier, that the galaxies are distributed in a very clumpy way. The big question at the time was, how could the galaxies grow so, matter in galaxies get so clumpy without disturbing the radiation? In particular, if you want to gather plasma together to make the start of galaxies, you're going to drag radiation with it. It's going to cause a mess. It was, in fact, said by many in the early 80s that there's a crisis in cosmology. We can't understand why the radiation is so smooth. That led me, in 1982, to introduce the notion of non-baryonic dark matter. Dark matter that is dark because it doesn't interact, at least very strongly, with ordinary matter, baryonic matter, or with radiation. If it didn't interact with radiation, then the dark matter could slip through the radiation and plasma and start to build concentrations of matter without disturbing the radiation very much. So those were the pieces we had when Jerry Yu and I put together the notion of evolution of the distribution of matter in the early universe, the development of these oscillations. This is too technical. Let's go on to the present situation. You look at the distribution of the radiation temperature across the sky. It's measured with dazzlingly great precision. You analyze that distribution into the amount of its variation as a function of angular position across the sky. You get this distinct pattern. You look at the large-scale distribution of galaxies, you get another quite distinctive pattern. You look at the line that you can see in the bottom figure, and you can't make out in the top figure because it's totally obscured by the symbols. The fit is so good. These are the distributions of radiation and baryonic matter you would expect if the universe expanded from a hot Big Bang. If its mass was dominated by that non-baryonic cold dark matter I introduced in 1982, and if there is also that cosmological constant that I argued for in 1984. Beautiful theory. I don't know how much time I've been spending, but let me just wrap up. I didn't mean to do that yet. Beautiful fit. We have in cosmology two sides to the situation. On the one side, wonderful agreement between theory and measurement, as exemplified here, and I could go on at some length. There is one anomaly that bothers people these days. The distance scale in cosmology can be said in two ways. You can measure distances to nearby galaxies and measure their redshifts and find the expansion rates, or you can make the fit to these measurements. The fit to these measurements requires an expansion rate that is 10% larger than what you get by astronomers' measurements of distances. There's two lines of thought on that, sometimes endorsed both by the same people. First, the theory works so well, it must be working here too. Surely there's a systematic error in the astronomers' distance measurements. Except, of course, the astronomers have done an excellent job. And if they've made a mistake, it's a pretty subtle one. On the other hand, if there is a true anomaly, it will mean that the theory has got to be adjusted. I certainly don't think that this theory is going to have to be abandoned. But you bear in mind that I made it up in 1982 out of the simplest pieces I thought I could get away with. It's held up pretty well, but it would be not at all surprising if some of those pieces had to be adjusted. And it would be exciting to see a real anomaly that will guide us to an adjustment that will make a still better cosmology. As I emphasized on the right, we're also in the curious situation that this theory that I'm touting involves two hypothetical notions. First, that 25% is wrong. It should be 75%. First, there's this hypothetical non-baryonic dark matter, and second, there's Einstein's cosmological constant. That got a new name in recent years. I certainly didn't do it. Called it dark energy. People like the name. It's widely used, but it's kind of it's public relations. Nothing has happened. We still don't understand lambda. It got a better name, but that hasn't changed anything. But pretty good situation. So I should just like to conclude with a quote by a native philosopher, brilliant philosopher and expert on baseball, Yogi Berra, who is alleged to have said, and he said so many interesting things that you can never be sure, you can see a lot by just looking. You can see a lot in science by just looking. In astronomy and cosmology, a lot of people have looked. You see a random selection of them here. And we collectively, have learned a lot by just looking at the universe. So, now I think I can go back to No. Can I somehow, share? Is that what I want to do? I want to get out of here and see if there are any questions. How do I check? Share screen. The shared window is closed. Can I get back to you guys?
Yes. So there's a small button which says stop sharing.
Well, I have one. Oh, stop video or stop. No, I have share screen.
Right. So you've stopped actually sharing the screen, so we can see your face now.
Oh, have I? Okay, I can't see your face.
Okay, I'll just start my video.
Oh, I see my face. Well, all right.
Right. So thank you so much. I think we do have a few questions if you have the time to take them.
Of course.
So just letting everybody know, so we have about 29 participants. There were 33 and then some people had to leave. So you could do it this two ways. You can either send a chat and then I can read out the question, or I can actually have you, I can allow you to I'll give you I'll give you the microphone and then you can ask the question yourself. Okay, so let me just go to Juliana, and I'm going to allow you to talk. So now you can speak.
I see the question. Shall I repeat it? Or you can all see it. Right. And I will say, no, this is not going to work because the radiation is smoothly distributed. It didn't come, as far as we can tell, from localized sources like supernovae. Instead, it's everywhere, smoothly distributed. You could ask, where did it come from?
Yeah, but the whole universe was like that. The whole universe was just trying to form stars, and you have this hydrogen just sitting there, who knows for how long, and it's hot, and it's starting to form stars, and stars don't know how to form. There is no magnetic field. There is nothing to make the stars be smaller or what we call a stable size. And all of a sudden you have this tremendous explosions and instabilities, and that would have caused a temperature. I know it's 3000 Kelvin for what we think the temperature of the universe was back then, when the radiation from matter. So I'm just thinking of other avenues for. It's just a question, of course.
Of course, and it's good to ask these questions and to think independently. But you know, we have helium that would have been produced when the temperature was about 10 to the 9th Kelvin in abundance, along with deuterium, that agrees pretty well with what's observed today. It looks like it's an expansion from a very high temperature. There was 25 years ago, there was the thought maybe this radiation was produced not in the early universe, but in exploding stars at more modest times where the density was less high. That idea worked for a while, but it has got to be ruled out on many grounds. Most directly, I think, on the simple point that the CMB, the radiation, is very smoothly distributed. Parts in 10 to the 6th, parts in a million fluctuations. Known supernovae are much more sparsely distributed. They wouldn't add up to such a smooth distribution. And as I say, to understand the origin of helium and to understand those oscillations you saw, we need expansion from very high temperature. Don't want to be didactic.
We have another question from Susan.
Okay.
Susan, you can speak now. Just unmute yourself.
Sorry, I don't have a question at the moment. I had accidentally clicked on the raise hand icon, so.
That's okay, thank you.
I do that often.
Okay, so let me go to then Steve Pellerin.
Hi, Dr. Peebles. Fantastic talk. I really enjoyed listening to you, especially the stories you had about some of your colleagues. That's fantastic. I did have a question for you about.
I'm trying to make this thing louder and I can't. There it goes.
Okay, if I talk a little bit more, can
Oh,
you hear
but
me?
no, I'm loud now. I can hear you.
Okay, all right, great.
Maybe you could start again.
Sure. I was just saying I really enjoyed listening to your talk and your anecdotal stories about your colleagues and that's fantastic. I really enjoyed that. I would say I noticed in your last couple comments there that you were talking about your theory from the 1980s and how, you know, studying a few anomalies might help you or might help us to maybe refine some of your ideas. Has some of the newer technology that we've had in our space telescopes, the ones especially that are looking at the cosmic microwave background, with their higher and higher resolution, each new generation of space telescope seems to give us a more refined look at the irregularities in that microwave background. Is that going to be where you're going to find these anomalies?
Well, there's a good shot we'll find it there. As you say, technology has played a very important role in all of this. We wouldn't have nearly the evidence we have if it weren't for the development of technology for other purposes. I like to make the point that the Bell Labs back in the late 50s were investigating communication by microwave radiation. That plus a whole lot of technology gave us those cell phones that it bothers me to see when people walk around looking at their cell phones instead of where they're going. But clever people took technology developed for such purposes as that and turned them to astronomy with magnificent results. That's continuing. There are big projects going on to look at the radiation in ever greater detail, to map out the large-scale distribution of galaxies in ever greater detail. We may get lucky and see an anomaly, an observation that doesn't fit with the theory that will guide us to a better theory. As I said, I find it hard to imagine the theory is dead wrong, but equally hard to imagine that it's the final theory. Of course, we have still the great question, what is the nature of that dark matter? Big experiments in progress trying to detect the interaction of dark matter with ordinary baryonic matter in the laboratory by the occasional collision of a dark matter particle with a baryon. Ever increasing precision, beautiful experiments going on in that Sudbury mine in Ontario. Oh, you're in Ontario. We'll see what happens. We may be surprised at any day now.
Okay, are there other questions? You could either raise your hand so I could know that to allow you to talk, or you could write it in the chat window, or you could put it in the Q&A window. Okay, Juliana has another question.
Okay.
Go ahead, Juliana.
I want to mention something that the Sudbury Observatory also already resolved a big problem in astronomy, the solar neutrino problem that I was involved with because I had a thesis about solar neutrinos, and that should make us very proud, us Canadians, that we were able to resolve an incredible problem that lasted forever, basically.
You're right. That was a magnificent accomplishment. Art McDonald was a leader on that at Kingston, Queen's University, Kingston. I might just tell you, a side remark, when I was an undergraduate, I and some friends drove east to jobs in Ottawa. We passed Sudbury. It was then a very active producer of nickel, mainly, along with other metals. In those days, although Canada boasts about its care for the environment, there was no care. The refinery just dumped all the debris, the noxious gases, out the chimney. The result was that for a long distance around Sudbury, everything was black, nothing green. Truly amazing mess. I am cheered to see that these days an image of Sudbury shows everything is green. People at last recognized that we shouldn't pollute the planet, and steps were taken. That mine still operates, still refining, still producing nickel, and not polluting. And of course, it is a supremely effective laboratory for many experiments, including the search for dark matter. Yes, Canada can be very proud of that observatory, and they could bear in mind the lesson. We should have been more careful in the past.
Thank you. Thomas Sobokan has a question, so you can speak, Thomas.
Thank you very much, Dr. Peebles. Your talk was fascinating. What do you see as the future of cosmology? What direction is it going in these days? Thank you.
Thank you, Thomas. Several directions. First, there is the question, what was the universe doing before it was expanding? Of course, there are people working hard on that. It's a tough problem because we have precious little evidence to guide us to what was happening. But that doesn't stop a good theorist. They will invent ideas, and they will hope, it often happens, that predictions will come up that can be verified or shown to be wrong. That's going to continue. Precision measurements of the microwave background and of the galaxy distributions are ongoing, and we may expect they will show us new things. We will see. The cosmological constant is really an ugly thing from the point of view of quantum mechanics, because the only natural version of the cosmological constant, vacuum energy density, is ridiculously big compared to what's wanted. That leads to the thought, maybe the cosmological constant isn't a constant, not an ugly constant of nature, but rather a dynamical variable, a quantity that's evolving as the universe expands. I've written on that with Berat Ratra. Nowadays, there is a big program to see whether the cosmological constant is changing with time. If it is, it's an exciting new research opportunity, show how that dynamical entity fits in with all of the other dynamics in our well-tested experimental physics. Myself, I am particularly fascinated by galaxies these days. With the Standard Model, people can make good computations of how mass would be evolving, how it may collect in galaxies, and what the galaxies would look like. I'm very impressed by the progress they've made, but also kind of interested in the difficulties they've encountered. In particular, many galaxies are nearly pure disks of the sort you saw in M101, that nearby galaxy where I spent a little time talking about the color and the number of planets. Those kind of galaxies don't seem to naturally come out of the standard theory. I'm just finishing a paper, highly speculative, on how the theory, the cosmology that is so well tested, might be twiddled a bit, might be adjusted to better account for the presence of these near pure disk galaxies. So I guess the answer to your question is you look in every direction you can, and maybe you'll get lucky. It's happened time and again.
Thank you. I have Steve Pellerin, who is asking another question.
Hi again, Dr. Peebles. I was just wondering, what would you consider to have been so far the most challenging aspect of your research in cosmology? What was it that gave you fits?
Well, of course, I mentioned that when I started on this subject, it had precious little evidence and far more ideas than evidence. I didn't like that at all. How did we know? In fact, you know, there's a saying we sometimes have in physics about just so stories. You remember how the leopard got its spots and such things? Cosmology looked to me like a just so story. You made up a picture that fit the few observations we have. And you said, well, this is a good picture for the universe. Why is it a good picture? You didn't have much evidence, you just made that up. That was my impression as a graduate student. I wasn't much more favorably inclined to cosmology when Bob Dickey suggested I look into it. But there is a physicist with a very good instinct for interesting things to do. When I started looking into the theory, I found things to do, as I said, and that led to more. So most challenging clearly was getting started. Through the years, you know, well, you know, cosmologists, as in any group, no matter how scientifically inclined, have opinions that aren't entirely rational. In the 1980s and through much of the 1990s, there was a fixed notion among many of my colleagues that the universe is expanding at just at escape velocity. You understand that's the rate at which the gravity is always slowing the expansion, but never quite stopping it. On and on, the expansion slows ever more, but continues expanding. That's kind of a nice situation because when we as a civilization flourished and decided to take a look at the rate of expansion of the universe, we'd find it's at escape velocity, no matter when we flourished. That's kind of neat. It's an idea I used to like too. In the 1980s, I was pretty convinced it's wrong. We need that lambda. We're expanding it faster than escape velocity. Getting people to pay attention to that was not so much difficult as, well, I must admit, it was sort of confusing. I loved an experience talking to a bright young astronomer, cosmologist in the, I think about 1990, who said, "You're only doing that to annoy. Do you remember Alice in Wonderland? He only does it to annoy because he knows it teases." That was my feeling in those days. I got to go to meetings and hear lectures on why the universe has escape velocity just, and I would be able to speak up and say, but that's not what the evidence says. The evidence was not by no means straightforward. It was only a hunch, my interpretation of what's reasonable. But it was kind of fun always to remind people of this evidence. And in fact, most of them just forgot it, so that at the next meeting, I could repeat the evidence and it all seemed new. It wasn't so much challenging as, well, I had to wait for people to catch up, and they did. Most challenging now, well, you know, I'm retired. I still go in, well, I still do work. I was about to say I still go into the lab, but that stopped for the moment. Challenging, no, well, everything is challenging. I don't think I would want to rank any more heavily than that.
I think we're well past the hour mark, so perhaps we should wrap up. If Randy would like to take over.
Hi, Randy.
Hi, Dr. Peebles. Such a pleasure, such an honor to have you here this afternoon. Not just for what you've told us about cosmology, but the personal insights. You've had over half a century of knowledge and experience, the people you've known. Just tremendous listening to you today. And is it too late to wish a happy birthday? I believe you had a birthday, a milestone birthday on Saturday, your 85th. Congratulations on that.
Thank you.
And we look forward to many more years. We need you and others like you working and doing what you're doing. So even if you knock on that door at the lab, and I'm sure that it'll open if any day you want to go in there.
Right.
While I'm on, I'll also thank, if you don't mind, Nick Baker and Mark Lubrick from the Office of Open Learning at the University of Windsor for their help in today's presentation. And of course, you too, Chitra. It's been, you've done a lot over the last few days to bring this together as well, and we all appreciate that. And thanks also to all the RASC Windsor Center members that were here today. We'll long remember this, I can assure you. Thanks again.
My pleasure.